Hello again, students, and welcome to a new nugget on biomass for energy. This lesson deals with the system solutions, and we shall now have a look at how extensive biomass utilization might influence the soil productivity in the long run. The thing is that in traditional farming, and the same is true for silviculture, was part of the organic matter left during the harvesting operation. But when we want to use the residues, those parts of the plants that are not the primary product for energy, then we no longer leave these parts. So what we do is to extract more material from the harvested area. And that also means that we take much bigger amounts of nutrients away from the soil. So in the long run, we may well deplete the soil of essential elements and hence reduce its productivity. This may not happen, since the whole idea of biomass for energy use is to make society more sustainable. So methods for nutrients and mineral circulation must be included in the biomass for energy system. So let's have a look at that aspect. The first thing to know is which elements are crucial, and that comes back to the fundamental biology. In case you do not have a good biology textbook handy on your desk or in your bookshelves, I'd recommend you go to the website libretext.org. Then open the menu tab, explore the libraries, and go on to bookshelves, and then go on to Introductory and General Biology. Open the book General Biology, Boundless. Go to chapter 31, Soil and Plant Nutrition, and work your way through sections A, B, and C. You will notice that the texts are short, but they are important. As you see in the table to the left, what a plant needs to grow, besides solar energy and water, is actually only a few number of chemical substances. That is of course not all true, because plants consist of cells, just like other living matter, and cells come from cells. So there has to be a cell structure too, a structure to take care of these elements and organize their interaction. But right now we will concentrate on the elements as such. The table is not complete, because there is also a set of trace elements that are needed, but the most important elements are listed in the table. So let us first look at where from the plant will take these elements. For that, you have to look in text section 31.2 in the biology book, and this text section is dedicated to the soil. The figure in this slide is copied from text section 31.2a in the book, and shows the main categories of material in the soil. It is obvious that most of the elements must be supplied from the soil, while you are, of course, well aware that a significant amount of carbon is also taken from the atmosphere in the photosynthesis process. In case you are not familiar with the photosynthesis, I'd want to refer you back to the first lesson in this course, or go through chapter 8 in the biology textbook. So basically, the soil must contain sufficient amounts of the elements listed in the table in the previous slide. Let us now have a look at the proportions of different elements in some representative plants. We will now make use of the Phyllis Biomass database, and we will access it via the main course book for this entire course, namely the BusyPlan Handbook. So go to the web page bioenergyprof.eu and open Basics, and go down a bit in the text to find a link to BusyPlan. At the bottom of the BusyPlan page, you will find the main textbook for the entire course in a tabular structure. But right now we are only interested in the Phyllis database, which is found in the right-hand side column of the page. What I've done here is to choose to search for eucalyptus, just to show you how it works. Scrolling down the left side, you will find that there are lots of different samples, like kraft lignin from eucalyptus, bark, char and such. But what I've done is to select 21 samples of stem wood and then asked Phyllis to present the average values. If you do not know Phyllis, I advise you to go through it and learn to use it. Let's now look at what we have found. First, the proximate analysis, water, ash, volatiles and such. These are given in weight % of the dry ash-free substance. The little diagrams to the far right shows how the samples are distributed from minimum to maximum as presented in the table. Then there is the ultimate analysis: carbon, hydrogen, nitrogen, sulfur and oxygen. Following the heating values, we find the major elements, and these are given in milligrams per kilo dry substance. Following this comes the minor elements, again milligrams per kilo of dry substance. And at the bottom is the ash composition. This is expressed as oxides, and the proportions are weight % of the ash. So let us look at these values and how they can be used. We start from 1 kilo of wet material with 11.1% moisture content. So that means 111 grams of water and hence 889 grams of dry substance. And then 1.39% of the dry substance is ash, which is 12.36 grams. This leaves 876.64 grams of dry and ash-free substance. Now we look at the ultimate analysis. Since the numbers are rounded, we will find the sum 99.8%, but we accept that. So the ultimate analysis is expressed as % of the dry ash-free substance, and we can compute the amounts of the elements. We now find a deficit of 1.75 grams. So that is the 0.2%. And now we continue. For the chemical analysis, you have to be very careful when calculating. The problem is that the basis for different elements in some cases, like for chlorine in this example, is expressed in milligrams per kilo dry and ash-free substance. But for the other elements, is the content expressed as milligrams per kilo of dry substance. It is obvious that a calculation like this, based on rounded average numbers, will never balance perfectly. But like all other estimates in the present lesson, is the main aim not to find accurate theoretical values, but to get the overall picture. So let us now look at a few elements and set up the mass balance when 1 kilo of wet material is extracted from a certain area. In this slide have I put up the amounts of some elements that are withdrawn as 1 kilo of wet material is extracted from a land area. The elements are the ones that were presented as essential in the first slide, except for oxygen and hydrogen. A major reason for that is that hydrogen and oxygen to the main part are supplied from carbon dioxide and from water. Carbon is also supplied from the atmosphere to a great extent, but the reason to include it in the removal is because the carbon balance in the soil is also crucial. So let us now see what is left in the ashes. Go back to the Phyllis data and compute how much of each element is present in the ash. Now you have to be able to recalculate the amount of a certain element when it is present in the form of an oxide. So you have to be able to do a simple chemical calculation based on atomic weights. That means you might have to consult the periodic table of the elements. I will not go through this, but the slide gives you the results. So now we are here. We are not home yet, But as you can see, will returning the ash significantly improve the mass balances, except for carbon, nitrogen and sulfur. The carbon balance in the soil is most crucial for the microorganisms actually living there, because the eucalyptus tree itself will get its main supply of carbon from the atmosphere. So the carbon deficit in the soil is by no means represented by the number in this slide. But the microorganisms in the soil are crucial for the soil quality. So the carbon balance must also be considered, though it cannot be treated the way I do it here. Supplying sulfur may pose problems, but let us first look at the nitrogen balance. Now go to the OECD homepage and work your way through the environmental indicators for agriculture. Here you will find links to nitrogen and to phosphorus balances on a national level. Not all countries in the world are included, but quite a few are. Now, one thing you have to understand is that these data are for agriculture, not for silviculture. In agriculture, you would use fertilizers, but not in silviculture. In agriculture, you would spread manure, but not in silviculture. And there are lots of other differences. But we may assume that the atmospheric deposition is the same or at least similar on both types of land. So what I've done here is I've gone into general statistics for agriculture and fisheries, environmental indicators, and then selected nitrogen balance. And then I've taken Australia as an example. For dates, I've decided to use the data from 2015 for Australia, as I said. So let's go back to the left-hand side column and see what can be found there. At the top, we have the total fertilizers added to the land. But this is agricultural land, and what we are looking at is silvicultural land. So there's no fertilizers and no input of manure. But what we have is atmospheric deposition on the land. And so let's go to 2015 and see how many tons of atmospheric deposition of nitrogen did we have at that time, during that year. And then we go back again to the bottom of the table. I close this to make space for the bottom of the table, and down here you see the total balance in tons and the acreage, the kilograms per hectare on average. So we go to 2015 again, we find the total tons and 19.8 kilos per hectare on average. Total tons is more than 7.6 million tons. Now we'll use these numbers to do the calculation. Finally, we have to make an assumption about the growth rate. I set 15 tons of dry substance per hectare and year, but I do not know this. When you do a balance for a region, you know you will have to find a proper number. But I just want to show you how to go about. So now we can compute the balance number, which becomes an addition of 0.9 grams per kilo of dry substance. And then this becomes the final balance. This will look different in different countries and with different crops. You will realize that the mass balance presented here is by no means complete, and that the numbers are very rough. But the only things I want to show you by this are these. First, the whole supply system is based on the fact that biomass is renewable. It is, yes, but only if the soil is not depleted of its nutrients. Second, I assume that you, who take this course, are engineers or energy planners. I do not think that there are so many biologists taking this course. But you do not have to be a biologist to be able to make a rough estimate. Once you've done this estimate, I would advise you to consult a biologist. But if you bring your own estimate to the biologist and use that to start the discussion and the consultation, it will improve the quality of the consultation, and you will be able to get much better advice on how to organize the system. So now you have an idea on how a very, very simple and rough mass balance can be made. You have an idea on why you shall do it, and that is to prepare yourself before you consult a biologist about what measures to take to maintain the nutrient balance. And now it's time for you to go on to the homework of this nugget.